Hello, everyone. Thanks for coming to my talk. And also thank for all the organizers for this PyCon Elite 1. It's my first time here and it has been fantastic. So thank you also for all the organizers for the great work. So onwards to my talk, I will talk about RAG systems, specifically on how to improve RAG systems. Just a bit about myself. So I'm originally from Lisbon, from Portugal. But I've been living the last years in Berlin, in Germany, and I've been working for a company called DeepSet, which is the company behind the Haystack, an open source framework to build RAG systems, complex information search systems, also now with agents, and yeah, it was also this framework that I used to present some of the work that I'm going to show here. So let's go into information retrieval. So what happens with the classic information retrieval problem? You have a query, you have some information need, and there's a document collection which potentially has text that answers to your information need or to your query. So typically what one does, one sends the query to the document collection and then in return gets snippets of documents, multiple documents that one needs to read through in order to find an answer for the question that you're making. And sometimes this is not easy. You have good results, but you still have to read through them all and understand everything. So what if we just replace the human at the end that reads the documents simply by an LLM? And ideally, we could just send part of the documents that the system returned to us together with the query to the LLM. We compose it in a nice prompt, and then the LLM ideally will give us the answer. So this is essentially in a nutshell what a RAG system is. Being a bit more technical, you have these models, you have a query, then you have a retriever which interprets the query, is connected with the document store or a vector database from where you retrieve documents. You compose the documents or parts of the documents in a prompt together with the query, which you feed into the LLM. And then with that, the LLM ideally will generate the answer for your question. There are many things here that you can tune and play around with parameters. You can change the prompt, obviously. You can also sometimes change some parameters of the LLM if it's behind an API, like the temperature, the number of tokens. But for today, let's just focus on this part, on the retriever. Let's see how we can retrieve documents and index documents in different ways. So a baseline retrieval method is essentially just this. You have a document, the document was split into chunks. Those chunks might be embedded into embedding space. They are indexed in the database. And when we have a query, you either query just by word if you don't use embeddings, or you find an embedding similarity, you retrieve chunks or full documents, and you present it to the user. This is like the baseline system to retrieval. But maybe we can do much better than that. And that's what I'm going to talk about. So I will firstly present some classical retrieval techniques, then some retrieval techniques, new ones based on LLMs. I will then just do a comparative summary of all these, because there are a few, around 7. And I will end up with showing an experiment where I run an annotated data set through all these techniques and I measure the scores that they have and the different results. So let's go. First, for the classical techniques, the first one is the sentence window retrieval. Let's jump into that one. And it's an easy to understand and to implement, I guess. So the idea here is that when you have a query and you retrieve the chunks that match that query, instead of returning only the chunks, you also return a context surrounding those chunks. So here, instead of returning only the chunk 1, 8, and 5, you also return the chunk 2, 7, and 9, 4, and 6. The idea here is to gather more context around the text that matched the user query. The only thing here is that when you pre-process your documents and when you index them, you need to find a way to preserve the order. So given any chunk, you know exactly what chunk comes before or comes after. It's the sentence window retrieval. Another technique, auto-merging retrieval. This is also involves some pre-processing of the documents. You have to transform your documents into this hierarchical tree structure. There are many ways to do this. Let's imagine that a simple way to do is to split the document into paragraphs, and then you split the paragraphs into sentences, and you have a hierarchical structure. And then the idea here is that you're only going to use for retrieval or for indexing and retrieval the leaf nodes, in this case the sentences at the bottom of the tree. So those are going to be indexed and also going to be used with your query. So your query is going to be made against these sentences. And the idea is that when you make a query, you also send a threshold. And what is that threshold used for? A query can match, in this case, several sentences. And the idea is that if at least, in this case, more than half of the sentences below a paragraph match your query, instead of returning the sentences, you return the whole paragraph. And otherwise, you just return the single sentence. But this is essentially another way to gather more context around the document. You transform the indexing structure so that when you match a query, you have something that's related with the query but doesn't implicitly match the query. But you get more context that you pass, in this case, to the LLM. So the second one, auto-merging retrieval. Let's go to the next one. So the next one is called maximum marginal relevance. This is a technique. It's old, and I would say it's more a re-ranking technique. It comes from the classic information retrieval times, and the idea here is what we see before is that the classical retrieval ranking techniques simply rank a query by similarity, the document by similarity to the query. But what happens if you have a high number of similar documents in the collection, or they are very redundant and you can even have duplicate information? So the idea here is to, after you retrieve, let's say 5 or 10 documents, you want to re-rank them in a way that the documents are relevant to the query and they're also new according to the documents that you already retrieved. So that the document that comes in the first place is very similar to the query. The one that comes in second place is very similar to the query, but not similar to the previous document that was already retrieved. How do you achieve this? You achieve this by scoring each of the documents, and there's a formula to rank them. This looks big, but let's just break it down quickly. It has essentially two things you need to compute. Let's look at the part inside square brackets. So the first, you simply compute the similarity between a query and the document. And then the second part, this is given, imagine that you already retrieved 5 documents and now you want to rank them. So you still haven't retrieved any one. So the first one, you get the one more similarly to the query with this formula. And then the second part is used to measure how similar is a document compared to the documents already retrieved, and you take the max of this. In the first case, since you only retrieved you didn't retrieve any documents, this will be 0. In the other cases, we have to compare each document with the documents already retrieved, and you take the one that has the maximum similarity, but because of the minus there, this will count as dissimilarity. You also noticed so this is penalized documents that are similar to the ones that are already retrieved. You also notice there's a parameter there, lambda, which essentially just works as a knob. If you want to give more weight to similarity to the query, or if you want to give more weight to dissimilarity with the already retrieved documents. And then you have to do this for all the documents that were still not ranked or retrieved. But the goal essentially here is a document should be relevant to the user's query and have minimal similarity to the previous selected documents. And you ranked the documents according to this score. Maximum marginal relevance. Let's now see one more classic technique, the last one. Hybrid retrieval. This technique essentially combines 2 methods of retrieving. One is based on keyword filtering. So until 2012, 2013, I guess, all these text representation methods was based on TF, IDF, weighted vectors, and BM25 algorithms for retrieval. And afterwards, people start to use embeddings to represent documents. So what this technique does is you have the same documents indexed in the old way of representing documents, essentially with keywords, and you also have the embeddings. And when you have a user query, you use them to query both vector stores or both databases. And you have the results, and then you can also re-rank them, or you can just send them to the user as is. This is a use case is, for instance, useful when you imagine, for instance, e-commerce platforms, where some people might specify a product by its name or feature or the model. So the keyword search here is very useful. Or some, they all just give a vague description of the product, where the semantic similarity might be beneficial. But you combine these two techniques and you have the hybrid retrieval method. So this is with the classic techniques, these four. Let's now go into the LLM-based techniques. I will present three. What they have in common is they all need an LLM to pre-process the query or pre-process the indexing of the documents. And that's what makes them special. So the first one, I would classify this one probably as a re-ranking technique, multi-query. So what you do here, when you have a user query, you want to expand this query. You can do one thing, which is you ask the LLM that given this user query, you want the LLM to give, let's say, 2 or 3 suggestions of similar queries by different words. That is, they have the same semantics, but they express it in the different word, and you end up with 3 vectors. And then what you do with this is you just use these vectors to query your document store and get the chunks. This is one way, let's say, to increase the recall. You probably will get you have more diverse expressions that might fetch documents from the database or chunks that your original query would not fetch. One way to see this multi-query is to see it in the other way around. Is instead of finding synonyms for your query, imagine if you have a very complex query, you might want to ask the LLM to break down a complex query in 2 or 3 questions that make up the final question. And this is another way to see the multi-query approach. Let's go for the next one. No, okay. At the end, you can also re-ranking. I keep this. When you get the results, you can re-rank them according to whatever mechanism you want, or you can just use them as they are. So the hypothetical document embedding height. This idea came in a paper, I think, from 2022 or 23, if I'm not sure. And the idea here is also to do some kind of query reformulation. So what you do is when you have a user query, you ask the LLM to generate a hypothetical document, a short sentence or a short paragraph that answers the user query. And then what you do is, instead of using the user query to fetch documents from the database, you take the documents generated by the LLM, or the short paragraphs or sentences, let's say, and you use the same embedding that you use to index the documents. And let's say in this case, you ask the LLM to embed 3 documents, you end up with 3 vectors. What you do is 3 vectors, you do average pooling. So you stack these vectors together, and then you take each dimension from each vector, you do the average, and you end up with a single vector. And then you'll use this vector to query the database. I see this as the approach before as also probably one technique to increase the recall. Probably here we end up with a more general embeddings that can fetch documents that contain the information for your query, but that your query doesn't explicitly mentions them. That's the hide approach. So document summary indexing. This is the last one based on LLMs, and the idea here is that you're going to build 2 indexes. The first index will only contain summaries of the original documents. So you're going to ask an LLM to generate a summary for every document that you have on your document collection, and you're going to build a vector database only with the summaries of your documents. But you also do the same thing as in the other approaches. You also chunk a document into other parts, and you also create an index only with chunks. So you have now 2 indexes, one with summaries of the documents and the other with chunks of the documents. When the user queries, what you do is you first throw your query against the summary index store, and what you get documents for which the summary matches the query of the user. And then what you do is you're going to use the references of those documents. So when you do the summaries, you also keep a reference to the original document, so that through that reference, you can get the original chunks of the document. And then you can select just the top 5 chunks that are more similar to the user query, or you can select all the chunks. But the idea is that you don't throw your query against the chunks of the document, you throw it against the summary, and then you use that to get the reference of the document where the summary comes from. I see this as a way to narrow down the results that you have. That if the summaries are good and your query is expressive, probably you only end up with 1 or 2 documents that actually have the information that you need, and the system doesn't start to grab stuff that's not relevant to your query. It doesn't answer your question. Okay, so this was a lot, 7, and I think I was a bit too fast, sorry, but let's just now wrap up what we saw. So I started with techniques that don't rely on LLM. You have the sentence window retrieval, that essentially you need a custom index structure just to keep the order of the chunks and you get the context. The auto merging, I would say, is something similar, but a bit more elaborated in the structure. The maximum margin relevance is just a re-ranking technique. It's just a way that you can, as you see here, you can apply re-ranking to any of these techniques. It's just a way to re-rank the return documents at the end. The hybrid retrieval, you combine 2 sources, the BM25 keyword filtering and semantic search. The multi-query and the hypothetical embeddings is a way to reformulate your query so that you have more expressive queries that you throw into against the database. And then the document summary indexing, for which you also need to build a custom data structure, and then you use those 2 data structures or these 2 databases on the query time. So what I did is I implemented all of these in Haystack. Well, some are already part of the core of Haystack, others I had to implement them. And then I wanted to see these things work. I want to see how these things, well, to test if the code works and see how they perform against some data sets. So I found this preprint from Archive, Advanced Rag Output Grading. The preprint contains a data set where the data are also archived preprints all around transformers and LLMs, so PDFs, around 13 PDF papers, and also together with the data set, there are around 100 questions for which were generated, the questions and the answers with an LLM, but they were all validated, the questions and the answers, manually by humans. So what you have a data set for which you have a question, you have the expected answer, and you have the PDF where the answer should come from. So what I did, I just fed this data set to each of these techniques, and then I compared the results that the RAG system with different retrieval methods would give. And I compared the answer that the system gave with the answer that was on the annotated data set, and I simply used the semantic similarity, answer similarity as metric. So I embedded both the annotated answer and the answer generated by the system into the same space, and you combine and you compute the cosine similarity in between those 2 vectors. So these were the results. Okay, the best one was the document summary indexing. Okay, I was not surprised because it's the one that also leverages more computational power, so I was expecting to give some good results. That was good to see that it happens. But I was also surprised to see that the hybrid retrieval and the sentence window retrieval, those simple techniques, they also gave very good results. Comparing, for instance, with the other 2 methods that also need LLMs and they are doing query reformulations. I didn't squeeze much into the... so this was more an ad hoc experiment. Of course, you can always play more with the parameters and try to come up and down with the scores. I used most of the default parameters that come in Haystack when I build these pipelines, and I just wanted to see the code working and see some differences in scores. But of course, one could now spend time and try to play around with the parameters and see how you can improve the scores on each metric. So I used the chunks were a 15 sentence, so I split the documents into chunks of 15 sentences each, and I used the top 3 as the retrieval, and the LLM for all the RAG systems here was the GPT-4 Mini. Some takeaways from this experience. I think it's always worth it to build a data set. I see many people building RAG systems and changing them, and they just throw away one question on another and see how that question changed. I think it's worth it to invest some time and just look at your data, come up with 50 questions and the answers that you should expect and the documents, and use that to start playing around with your experiences. Start with a simple basic approach, just the first slide I show with that retrieval method, nothing fancy, and you see what does the score. Keep that as the baseline, and then try to slowly progress. Go first to sentence window, hybrid, they gave good results. Still, if that is not satisfactory, then okay, start using these more complex things with LLMs. This is all available in Haystack. So as I said before, some of these retrieval methods are part of the core package. Others I had to implement by myself, meaning I had to select components, connect the components, define the pipeline run workflow for the data, and have them work. But since the last release of Haystack, we now have super components, meaning that these more elaborated pipelines to do RAG systems can be easily shared just with the YAML file. So we now have the feature that supports that. So you can just share. If someone does one of these pipelines, can easily share, and you can integrate even with other pipelines in a complex system. It's now available since Haystack 2.12. Just some references that I used for the work, and yeah, that's all from my presentation. This now failed, but you should see here the results for the. I had the QR codes, but they are not loading for some reason. But yeah, thanks for being here.
Does anyone have any question?
Oh, it's a pity that this doesn't load.
Thank you very much. The question is, most of the examples that you used were like heavy documents like PDFs, or that's what I understood. Have you seen, let's say that you have configuration files or more well-structured data that you want to generate through the LLM? Have you seen any of those techniques perform better in that manner?
What do you mean exactly? Like what will be the source of data?
Let's say that your library is like 1,000 JSON objects with the same structure, and given some user query, you would like to generate one JSON structure, one new one that should be inspired by those. Let's say that is defined.
Yeah. So you always need to have text that you can embed, or you have. I mean, depends what you're going to do as a query. I expect as a query you give as text. So whatever you extract your data from, you have to put it in a format which is text or something that's similar to what your query is. In Haystack, we have some converters that can convert PDFs to text, can convert tables which have text to a document from Haystack. We have all those converters. You can use them to try to build indexing for RAG systems. I hope that answers the question. Yeah.
I'm not very technical on RAGs, so maybe that's a stupid question. But one problem that our users report on our usage of LLM is that the streaming takes too long to start. How does that retrieval plays a role in overall runtime for the LLM to start? Is any one of those extremely more efficient to get started? Is that a factor on retrieval, or does retrieval not influence it that much?
It's a bit independent. If you look here, this is a different model, right? So the retriever is here, and the LLM can only start when you have the data from the retriever. So I would say those are completely independent steps. I mean, what can happen is that with the document summary indexing, you need to use an LLM to pre-process your documents. But you only need to do is this only once, and then you have the index. Then at runtime, the query, I imagine you have it's only you using that machine, so the retrieval should be fast than LLM. The LLM, I'm assuming you use an OPI, an open, so from OpenAI or from any other provider, so there's always more latency than comparing to the retrieval. But I would say the retrieval should be fast and should not be a bottleneck.
Okay,
Or
so
at
it
least
doesn't
if
play
you
a
have a
role.
bottleneck, probably should see why it is a bottleneck. It shouldn't be.
Retrieval. Okay, great. Thank you.
Thank you so much, David. If you have any more questions, please leave it in the chat. So now, yes,
Okay, thank you.
thank you so much, David.